All right, welcome back to another math task explanation, everyone. Today we're going to be looking at a practice criteria B. We have a task set out for us where we have a table of values we need to fill, and we have some diagrams that we can use to do that. So let's have a look. Almost immediately I can notice some patterns in this table. Probably I could even fill the table without looking at the diagrams, because if I look at column B, for example, the B values 1, 1, 2, 2, 3, 3, 4, 4. Well, guess what? Next up is
5, 5.
5, 5, 6, 6. For M, I have a half, 1, 1.5, 2. So these numbers go up by half every time. So we fill in the values 2.5 and 2.5, and then 3 and 3. Now N is slightly more complicated, I see. Although actually the right coordinate, the y coordinate, half, 1, 1.5, 2, this is the same as I did before. Half, 1, 1.5, 2, it becomes 2.5 and 3. But what about that x coordinate? What is the pattern that we observe? Would anyone care to share? Arsha?
It's adding by 1.5.
Adding 1.5 every time. Yes, so 1.5 plus 1.5 is 3, plus 1.5, 4.5, plus 1.5, 6, plus 1.5 giving 7.5, and then finally we're ending up at 9. The length of MO. Who sees the pattern for the length of MO? Yes.
It's like the outside number increases by 1.
The outside number, this number here, increases by 1 every time. We have a 2, a 3, a 4. So the next step is going to be 5 root 2 over 2, and then 6 root 2 over 2. Very well, we've completed the table, and these values relate to these lengths in the diagram, which we'll come back to in a moment. Okay, so then we are asked to find any general rules for the coordinates of B in terms of N. Well, that's easy. For B, the values were 1, 1, 2, 2, 3, 3. So N, comma, N. And for O, let's have another look at the O column. The O column is here. These values 1, 2, 3, 4, 5, 6. Those are exactly my N values. And 0, 0, 0, 0, 0, 0. What's the next one going to be? 0. So the general rule we find there, N, 0. So this is what they often ask you when they ask for a general rule in mathematics. They wanted you to express it in terms of a variable, in this case n. So these are all the answers you need to give in this question. To verify, oh, this is such an important word. When we're asking you to verify, it basically means check that the rule works by using a new value, one that wasn't given to you, but one that you calculated. So when it comes to the verify steps for these rules, these last two options for B are what we calculated. So they're fair game. We just cannot verify with anything that was already part of the problem to begin with. So in this case, let's just use the n value of 5 to do some verification. For n equals 5, okay, I pointed at B, but the coordinates are about O. We're doing the O rule. From the table, I can clearly see the coordinates of O are 6, 0. From my rule, n, 0, n, 0 becomes 6, 0 when n equals 6. Hey, what do I notice about these two? They are the same. Same answer. So the table method and my rule method both gave the same answer, and therefore this verifies that my rule is indeed giving me the same types of answers as my table would. So I can say it's verified. Now, an even more elegant solution would be not even to refer to the table, but to make a diagram for number 6. I think that I would like even more. So you can see there's a diagram here for number 4. We can do a diagram for number 5 or 6. Either one works. And you will then show that in your diagram, for instance, if we would continue this pattern, for this diagram, point B would end up there, and point 0 or point O would end up 1 to the right more. So we could say if we make a new diagram for n equals 5, we find the O value of 5, 0. If we make one more diagram, we'll find the O value 6, 0, also then verifying our rule. I see I made a mistake. They said we have to use n equals 6. So there we go. For n equals 6, this is what we have. And then we come to the most difficult part of the whole test. And this will always be the case. The most difficult part is at the end, because it will include something called a justify. And that's really tricky. But now we've done a simple pattern. Let's have a look at a more complex pattern here. The relationship between the coordinates of m and the value n, and also the length of MO and the value n. Okay, so there's two things to do here. Coordinates m and length MO. Let's just divide my paper up into two parts for now. On one side I'm going to investigate m. And on the other side, I'm in a moment going to investigate the length MO, but let's focus on m now. What do I notice as a pattern when it comes to the coordinate m? Well, that's where we said we go up by a half every time. The values increase by 1/2 each step. Now to find, that's what I describe the pattern. Now let's find a general rule or a general value for this coordinate m. So we have to use the n value here. And let's once again look at my table. How does the n value relate to there? How does this n value relate to there? How does this n value relate to there? Shreyas?
Like both coordinates are like half of n.
Yeah, very good. They're both half of this n value. A 2 becomes a 1. A 4 becomes a 2. A 6 becomes a 3. So we're halving my n value. So the rule would be m is given by half of n. Half of n. That's the m coordinates. That's my rule for the m coordinates, n over 2 and n over 2. So let's verify. What do I see in the table for n equals 6? I had the values 3, 3. And my rule for n equals 6 would be 6 over 2, 6 over 2, which is also 3, 3. So once again, the table and my rule are giving the same value. This verifies my rule. Then we get to the most difficult step of this whole thing, which is a justification. So can we mathematically justify why it has to be n over 2 and n over 2? Well, okay, for a justify we need to usually think a bit more mathematically. So let's have a look back at where this all comes from. Our diagrams. In these diagrams, how do I find, well, let's have a look at my final diagram because it's nice and big so I can draw on it. How do we find the coordinates of this M point? Well, how is it created? We make a circle with a radius of n, so it's getting bigger and bigger and bigger. This circle, every step, it starts small and it's going bigger and bigger. So both of these values are n. Now m is exactly halfway there. The x value is halfway from A to O. It's the middle there. Similarly, the height of this m value is also half the height of the total circle. Or sorry, not the half the height of the total circle, the half the height of the radius of this circle. So since both those values fully are n, since I'm halving them both, they're both n over 2. So now to make sure I write that down in a nice way, so let's write my justification. The height and well, not really width, let's say x value of m are both half of the radius, which is n. I could even say now, because I drew it in the sketch, I can say see diagram 4, because there I made some notes on diagram 4, so I can refer back to it. And therefore I can say, therefore x of m and y of m should both be n divided by 2. Now, when you go to MP5, or maybe even MP4 already, I'm not sure, you'll find that there you need to provide an official mathematical proof. So it needs to be very rigorous and set in stone. When we're justifying, we just have to explain with logic and mathematics why it's the case. So this is enough. You don't have to go into full proofs here. You can, of course, it's always allowed, but you don't have to. So next, let's look and investigate at the length of MO. What do we notice if we look back at our table of values? The length of MO starts at 1 root 2 over 2, 2 root 2 over 2, 3 root 2 over 2, 4 root 2 over 2. So actually we increase it by another root 2 over 2 every step. Increases by root 2 over 2 every step. So what is the rule that we see? Well, we already noticed it before. It's n root 2 over 2. That's the length of MO. So we can verify. And once again, we can use our table for n equals 6 to get 6 root 2 over 2. And we can also use our rule. And this is a bit boring because it's once again exactly the same, 6 root 2 over 2. But it verifies the value quite nicely. it verifies at least that our table value and our rule value match. It doesn't necessarily verify that our rule value matches the diagram. So if you want to do that, you'd have to link it back to the diagram still. And there's a very nice way for us to do so, because if we wanted to make another diagram for n equals 6, for instance, we would find that we draw a big triangle, because we don't have to draw the whole thing, only the MO part is of interest to us. We've already figured out that for n equals 6 from the table, these values are 3, 3 and 6, 0. And this length, MO, how can we find it? Well, we've learned this unit that we can use Pythagoras to find it. So we have a right angled triangle right here, where we have a length of 3 and a length of 3. So this diagonal length, let's call it C for a moment. We know that C squared is equal to 3 squared plus 3 squared. So C squared is equal to, let's do 9 plus 9, 18. So C is equal to the square root of 18. What is the square root of 18? Well, it's the square root of 2 times the square root of 9, which can be simplified to 3 times square root of 2. Now let's go back and compare to our other value here. These 6 root 2 over 2 can also be simplified to 3 times square root of 2. So you could also verify this with the diagram and see that they're the same. I would probably even prefer that. Finally, let's justify. The most mathematical part of the whole investigation is the justification step. So let's justify our rule of n times root 2 over 2. And here we once again go back to Pythagoras. If I use this little diagram here, we already discussed that this length is n over 2. We discussed that this length is n over 2. So once again we can make a Pythagoras equation to find the diagonal in this right angled triangle. Let me just bring that out. If I have n over 2 and n over 2, and I want to find this diagonal length from M to O, let's call this C, hypotenuse C. Oops. There we go. How do I find that? Oh, Pythagoras' theorem states, and let's properly write it where we want to write it. From diagram 4 and Pythagoras, we find n over 2 squared plus n over 2 squared is equal to our value C squared, so our MO value. Okay, n over 2 squared, that's n squared over 4 plus n squared over 4 is equal to C squared. Let's bring these together. We have 2n squared over 4 is equal to C squared. Hey, I can simplify. That's just divide by 2. N squared over 2 is equal to C squared. So C is equal to the square root of this. N squared over 2 all under a square root. This is not exactly what we needed to show, because we need to show a slightly different form of this, and we can get there if we split the square root. C is equal to n squared under a square root divided by 2 under a square root. Now n squared in a square root is equal to n. So we're left with n over square root of 2. And we need to now show that this is the same as 2 n root 2 over 2. So really what has happened is we need to multiply with an extra root 2 in the numerator to get our desired answer. But we are only allowed to do that if we also multiply the denominator by a square root of 2. And there we go, root 2 and n multiply, and root 2, and square root of 2 times square root of 2 cancels the square root, and we're left with 2. And this is indeed our rule that we needed to show. The length of MO is equal to that. This actually was a full proof, even more than justification. And there we go. We have finished the whole paper. I hope that was helpful. See you in a future video. Bye.